So, oops. Can I borrow this? Today is October 3rd, right? Okay. Can you print your name? Yeah. So everyone just print your name on that paper. Okay, let's get started. So last week, we talked about buffer overflow for the last 2 weeks. We were talking about buffer overflow. And last week, I showed you that there are many places we can inject our share code. But they are still on stack, actually. So we can inject the share code in the command line argument, which will be placed onto the stack by the shell. We can inject that in the environment variable, which is also on the stack of the program. So today, so far we have been overwriting the return address on the stack, and we totally ignored the saved frame pointer, which is saved EBP or saved RBP on the stack. We just put some random garbage in those 4 bytes or 8 bytes. We didn't care about that. So today we will say that what if we cannot overwrite the return address? We can only overwrite that saved EBP or RBP. We can still attack the program. And we start talking about different defenses for buffer overflow. So buffer overflow right now in the wild, it's very difficult to pull it off anymore because there are many different defense techniques. So today we are going to look at one of them. Next week we are going to look at more. So they are deployed in our real-world systems. Your laptop, your phones already have those kind of defense. So the first is those 2 share codes to print the flag. I just put it here, so later we may use it. Okay, so before we talk about those issues, I will first go over the Crack Me 4, the more difficult version of the program, the challenge. So how many of you solved this one? Okay, at least several of you here solved this one. So basically, this program, it has the same source code as the Crack Me 4. They're basically the same source code. This is a source code which you didn't have access to. But this source code is very similar to the one we looked at in the class. So there is a main function. The main function has a buffer. It checks how many command line arguments are there. You are supposed to give it another command line arguments, making it 2. Then there is a string copy to copy your command line argument to that buffer. So you can trigger a buffer overflow of the main function. Your goal is to jump to the print secret function. Okay, that's what I want you to do. Of course, to get a flag, you can directly jump to print flag. But I want to challenge yourself a little bit. Instead of jumping to print flag, you jump to print secret. So the easy version looks like this. This is Crack Me 4, the easy version, the same source code. It has a very pretty standard function prologue there. At the beginning, we have the endBR32, which is a secret feature we haven't talked about yet. After that is just the standard, the push EBP, move ESP to EBP, then subtract ESP with something to reserve some bytes for local variables. Then we have the harder version from the same source code. This is a harder version. We can say there are several instruction changes compared to this version. Some of you probably compared. They are the same source code, but with different compilation options. We have a little bit different binary program. So let's try to understand this. What's the purpose of this? How they are different? How do we hack this? Okay. Later I will show you the compilation options. Okay, so you can see the first instruction of this function, the main function, is not push EBP, move ESP to EBP anymore. Those are moved down here. The first instruction is actually load effective address ESP plus 4 to ECX. Okay, so at the very beginning of this function, like all other functions, ESP points to the return address. And above ESP, you have the parameters, arguments, right? So at the beginning of that, of this function, ESP points to the return address. So return address is where the main function returns it should return to. So it's probably in libc start main, because libc start main calls your main function if you are the developer. So the ESP points to here. So after this instruction, what happens is ECX has a new value. ECX now has ESP plus 4. Okay, we don't really know the value of ESP. We know ESP points to here. We don't know the concrete value of it. ESP is ECX now is ESP plus 4. That's it. Okay. After that, there is a very interesting instruction. We do a bitwise add operation on ESP and this constant, which is 7F and a 0. Okay. So that's a bitwise AND. So what will happen to ESP after this operation? So the most significant 7, so ESP is 4 bytes, right? In this case, ESP is 4 bytes. So the most significant 3 bytes of it will just do a bitwise AND with a bit 1, right? With 1. So it doesn't change. So the most significant 3 bytes do not change, stay the same. But the least significant byte, the half of that will change to 0. The other half stay the same because there is an F. So the purpose of this operation is just to make ESP aligned to 16 bytes boundary. That's basically the purpose of this. So the compiler inserted this to make the stack boundary of the main function aligned with a 16 bytes boundary. Why compiler is doing that? Maybe compiler believes that makes the program faster. Okay, that's maybe the reason. When you compile a program, you can choose. You can choose if you want that to be aligned with some boundary or not. Okay, so after that, we don't know, at the beginning, we don't know the ESP value. Now we know that ESP will move down to the closest boundary that align with 16 bytes. So, which means there will be a small area here. It's smaller than 16 bytes, but we don't really know how big it is, right? At least look at the disassembly code, we don't know how big it is. When we debug, we can find out. So after that, then we have a push ECX minus 4, the value at the memory location ECX minus 4, we push that to the memory again. And we know that ECX points to the argument. The ECX minus 4 actually points to return. So what we are doing is we are push another copy of this return address to the stack again. So after this, we have 2 copies of return address. The purpose of this is still, we want to make it look like this is the beginning of the main function's stack. We want it to be 16 bytes aligned. And we want to make it look like that, so we push another return address here. We do that. Now you say why we're using ECX, because when we do this, ESP has changed. ESP is not pointed to the return address anymore. So that's why we have an ECX points to here to have this. So after that, we have the standard push EBP, move ESP to EBP. So you can see after this, it looks like the stack starts from here. That's our ordinary stack layout. Looks like it starts from here. Okay. Then we have, because ECX may be used, the register may be used by other functions. The main function may call other functions. It may be used, so we have to save it. That's why we save it onto the stack to a push ECX. So after that, we call the function, call other function, do a lot of things. Here there is a string copy function. We can say that the string copy at this point, EBP points to here, and the buffer is actually at EBP minus 10. Okay, so that's why after save the EBP lower 4 bytes, we have saved the ECX. And at EBP minus 16 or 10 in hex, we have the buffer. So the buffer size is actually 12 bytes in this case, because we have 4 bytes of saved ECX. So after all the operations, we want to exit this main function. What happens is we're going to restore ECX from the stack to the register, and the ECX is at EBP minus 4. And we move that back to ECX. So after this, this is after this, then ECX points to this place again. EBP is not changed. Then we do a move EBP to ESP, then pop EBP. So after that, ESP where points to this return address, and ECX where points to somewhere. After that, we will load the effective address ECX minus 4 to ESP again. So after that, ESP actually points to the original return address. Okay. So even if we made a copy of this one at here, we never used this new copy. If you look at the binary code, you realize this copy was never used. There were 2 copies, but this copy was never used in this piece of code. Sometimes compiler does crazy things. Okay. Then after that, we just return. So to overwrite this one, what you need to overwrite is, if you want to overwrite the return address and return to print secret, okay, not print flag, print secret. We're going to return to here, print secret, not print flag. What you need to do is, the return address here, you need to set it as print secret. You need to figure out how big this buffer is. You can debug this program, you can figure it out. So there's another copy of the return address. Like I said, you don't have to set it. It's never used. When you overwrite this, you overwrite from the buffer, right? Everything above buffer you can overwrite. You only have one chance to overwrite this. What's interesting is you have to keep this saved ECX. If you do not have a correct saved ECX, because where the ESP is determined by the value of ECX. So if you do not have a correct saved ECX, then ESP will point to some other random address. You will not be able to point to your return secret. Okay, so that's the key. Let's say, then you put the 3 arguments up here, just like every other return to another function attack. This is obviously one way to overwrite this. And if you want to return to print flag, it's actually similar, right? You still need to override the return part. You just do not need to give the arguments, but you still have to have the correct ECX value here. So that's why you may need to debug the program to figure that out. Okay, any questions? Okay, then let me show you why the compiler is generating those 2 different versions of binary. Let me go to my GitHub. Let's see. So this one is Overflow level 4. So this is, oh no, sorry. We're looking at a crack me 4. Crack me 4 is just in a different folder. Same source code. That's a source code. I just showed you. Then here is a make file. The only difference is we give a different option here. You can say this is the easy version, the crack me for 32-bit. We give this option preferred stack boundary 2. 2 means 2 powers 2, 4 bytes. As long as it's aligned to 4 bytes, it's okay. Okay. This one is maybe 2 means 8, making 2 plus 1, I guess. I don't really remember because I think the hardware it should be 16 bytes, not 8 bytes. So look at here, the hard version, the difficult version, we didn't specify this. Then it has a default value, and the default value is either 3 or 4, which is the 16 bytes aligned. Okay, that's why compiler is generating those instructions. Okay, so that is the bonus question for the homework. You didn't have to get it in the exam. Well, probably we're not doing something like this. But if you are really analyzing real-world batteries, you will see a lot of crazy things. And the only way to understand what's going on is to debug, to read the disassembly. Okay, so the 64-bit version, the only way we can do it now is to directly return to flag, either return to the instruction here or return to the beginning of the return flag function. If you want to do print secret, setting up the arguments, then we have to use another approach called return-oriented programming, which we discuss the second half of the class. So using that approach, we will be able to set the registers because 64-bit version, the arguments are not on stack, they are in registers. Okay, so today we will talk about another attack. It's still a buffer overflow, it's still a stack-based sequential buffer overflow. We are still overflowing the buffer and something above the buffer, but today we will not have the chance to overwrite the return address. We will only be able to overwrite the frame pointer, which is a saved EBP, so 4 bytes lower than the return address. So far we have been ignoring that. We just put garbage there. Today we are going to say how we can just overwrite the saved EBP or RBP. So basically you need to understand the saved EBP or RBP, that is the address of the upper level functions stack, where that function stack is, right? And for that function, it also has a return address. So if you can manipulate the upper level functions return address, you can still return it to wherever you want. It's just that you are not changing the return address of the current function, but so the current function will return to the upper level, and when the upper level function returns, you return to your shellcode or something malicious. So the idea is to change upper level functions return address. So this is the example we're going to look at, and I call it Overflow 6. It's not overflow return because we're not directly overwriting the return address here. Main function, very simple. 2 command line arguments, then there is a val foo. Val foo takes 1 argument, which is your command line input. There is a buffer, 4 bytes in C code level. Then to make it very easy for you, I print out the buffer's address here. Obviously, in real world, you may not have the luxury to have the buffer's address, so you need to guess. But here, I print it out for you. Later, you will say why it makes things much easier. Then we just do a memory copy. We memory copy 12 bytes from your command line input to this buffer. Okay, 12 bytes. Then if we look at the binary of this program, this is a val foo function, standard function prolog here, push EBP, move, subtract. Then you can say something strange like call x86, get PC, thunk bx. Don't worry about that so far. Okay, those are to make this program runnable, this function runnable at any location. That's a compiler option called position independent code, PIC, position independent code, or position independent execution, PIE. Okay, basically it means this piece of program can be at any location of the address space. Okay, so they're not doing anything we need to worry about at this moment. Some of the functions we saw so far, they do not have that. That's because I disabled that part. Some of the functions we have, that's because I enabled that. So later we will discuss a difference called address space layout randomization. It means you can randomize the functions data in the address space. It can be anywhere. So to utilize that difference, you need the functions to be in position independent. So basically, those function calls are figuring out where it is at runtime. It's not determined at compile time. At runtime, it figures out where my function is at. Okay, so that's not something we need to worry about. If you look at the C code, I mean, it's very simple. So it will generate all things. Then there is a printf. After printf, we have this memory copy. So let's look at the memory copy here. That's where the vulnerability is. And the memory copy, we can say the first argument of that memory copy is in EAX, which is our target, the destination. And that is EBP minus 8, okay? Which means this is what the stack looks like. We have the argument P. We have a return address here. We have saved EBP. Then after that, so EBP points to saved EBP. Then after that, we have 8 bytes of buffer. So now we can only overwrite 12 bytes. We're overwriting here from here to save the EBP. That's it. We cannot overwrite return in this example, right? So if we can overwrite a return, then things are easy, like the examples we had last class. So that's what we can do. It's just this override save the EBP. Okay, so what will happen if I just give some garbage to save the EBP here? I still override it with garbage. What will happen? Segmentation fault, but before segmentation fault, what happens? What? So first of all, this is a Overflow function, right? So where the Overflow function returns successfully, right? It will, right? So when we return, Overflow will still return to the middle of main function, right? The main function, the problem is the main function where eventually at the end of Overflow, we are going to do a pop EBP. And that pop EBP is to restore the stack frame. So let's say EBP points to the stack frame of current function. So for Overflow, EBP points to here. So this is a stack frame of the function Overflow. And main function's stack frame will be somewhere up there. And that address is saved here in saved EBP and eventually restored in the EBP register. But we overwrite this one. So the main function, they cannot find its correct stack frame anymore. The main function where eventually when main function returns, it will return to where ESP points to, but that will be some garbage place, so that will generate the segment fault. Okay, so, but to fully understand how we can exploit this, now we know why it may generate a segment fault, but we don't want a segment fault, right? We want it to do something malicious. We want to get a flag. So to fully understand that, we need to analyze from here, fully understand what's going on here, okay? So let's say we're the attacker. We already do a buffer overflow. We overflow the buffer, which is 8 bytes. The value doesn't matter, okay? Then we overflow the saved EBP. Let's assume we overflow it with 4 letters, A's. Then when we do return, before return, the ESP points to the return address here, right? We didn't really change it. After return, the ESP, after return, first of all, is the return address here will move to EIP, which is in the middle of main function. And the ESP will move up 4 bytes. And the EBP has the saved EBP value. So EBP right now has the value 4/8. Okay, now we're going to the main function. We're going back to main function. Okay, look at here. This is a main function. That's a very simple main function. This main function, very simple one. Look at this main function here. We just made the function call to val-foo. Now we return to main function. So what does main function do? Remember, ESP at this point points to here, which is 4 bytes higher than P. Then EBP has the 4/8. Then the first thing we do is, ESP actually points to P. Now we add ESP 4 bytes to balance the stack, okay? Then after that, ESP points to here. After that, we move 0 to EAX. So EAX is basically the return value. So main function is going to return 0 in this case. So we're moving 0 to EAX for return value. Then after that, the main function will do a leave. So leave is equivalent to 2 instructions. Move EBP to ESP, then pop EBP. Okay, this is where interesting things happens. We already know this eventually triggers segment fault, but why? Okay, we already know that EBP right now has 4/8. Now we move EBP to ESP, then ESP in the first step, ESP will have 4/8. In the second step, we are popping to EBP. So where do we pop? We pop from where ESP points to. And ESP has a value 4/8. Okay? So basically we are dereferencing that 4/8. We use that 4/8 as an address, dereference that. So this is our first chance of segment fault, because that 4/8 may not be a valid address in the address space. When we dereference that, we may get a segment fault. Let's assume that works, okay? Let's assume there's no segment fault. What will happen is, because this is a pop operation, so EBP will have whatever is at that memory address. Then ESP will +4, because this is a pop. ESP will +4, right? So ESP now will points to AAAE +4 of that, okay? So this is what happened. So there is a chance for segment fault. That's the first chance of segment fault. Then after that, that's leave. Okay, then next we have return. So now ESP points to 3/8 and E. And the return will use that as an address and get whatever is there and put that into EIP, right? So that's our second chance of segment fault, because that AAAE may not be a valid address. Okay, so how can we exploit this so we can return to so we can get our flag? We cannot override the return, only this 4 bytes. So to get our flag, at this point, first of all, we need a share code, right? Our share code is 30 bytes something. We can put our share code on environment variable, so that's not a problem. We don't have to put the share code in the buffer. We put the share code in the environment variable. We get the address of the environment variable. But the problem is, eventually, this is what we are going to overwrite. We're going to overwrite EIP. Okay, how do we do that? Any idea? Okay, many ways to do that. I'll just show you one example. That's what I'm going to demo here. So one way to do that is we can override those 12 bytes. Then we get the address of the buffer. And we put the address of buffer in that saved EBP place. So let's assume that address is X. So So the saved EBP will have the address X. So what eventually EIP becomes to will be X plus 4 dereferenced. Okay? Which means where should we put our share code's address? We just put in the buffer 8 bytes, right? But those are 8 bytes. The address is only 4 bytes. We put the first 4 bytes or the second 4 bytes? Yeah, the upper 4 bytes. We put it actually. Sorry, my pointer is not working. Yeah, we actually put it here. Okay. Of course, you do not have to use X as here. You can use X 4 bytes lower. Then you can overwrite, put the address at the first 4 bytes. Okay, does that make sense? Are you following? Kind? Okay, so then let's try this. So this approach obviously works for both 32-bit and 64-bit. Where is our share code? Our share code is this one. 32-bit. Yeah, this is our share code. I may need this one. Using this one before. Okay, whatever. Okay, looks good. Let's make 1000 bytes select. Okay, this one looks good. Go to our server. We are looking at, we are looking at Overflow 6, 32-bit. So the first step is there is an issue, this one. The first step, we put the share code onto our stack. Then we get the rough address of our share code. What's the name? S code in this case. So that's our share code's address. We obviously need to add something there, but we have a big SNAT anyway, so that's easy. Then the program we're trying to hack, let's do a dump first. So that's the Overflow. You can say exactly the same program. I'm not using entire syntax. That's the same program. So the buffer is at EBP minus 8. Okay. So how do we construct our? Where is our share code again? Okay. So how do we? This one use command line arguments. So it will look like this. We're going to do a Python 2 print. We only have 12 bytes to write. If we write more than 12 bytes, doesn't really matter. Let's say if we overwrite 40 bytes, we will only get a segment fault. If we overwrite 8 bytes, then because there is a pending 0, so that's a segment fault. But if we do 7 bytes, when we do 7 bytes, how do we get a segment fault? Is that a pending 2 bytes there? What's going on here? no matter what we do, we get a segment fault. Even 1 byte, we get a segment fault. Okay. Okay, anyone can answer me why? No matter how many bytes we are giving there, it gets a segment fault. Why is that? Exactly. Here we're doing a memory copy. We're not doing a string copy. So we're always copying 12 bytes. So even though you're giving just 4 bytes, then there will be 8 bytes, maybe some zero there, some garbage there, and we're overwrite as that. So no matter what we give here, we get a segment fault. So what we're going to do is the first 4 bytes, that will be lower 4 bytes of the buffer. We don't need anything. Then after that 4 bytes, we will have the buffer's address, which we have here. We'll print it out for you. For it's 45 D2 FF. Now we are going to overwrite our saved EBP. Oh, sorry. The saved EBP should be here, actually. The saved EBP should point to our buffer, which is 54 D2 FF. And this 4 bytes should be our sharecode's address. So our sharecode here, we have a DAAD. We have a big sled, so AD we just change to DD. That's just to give us a chance to hit to the middle of that. So this is what our exploit look like. Let's try. Yeah, it works. So the other approach I said is, in this approach, what we're doing, whoops, where is it? Why is it jumping around? In this approach, what we're doing is we put saved EBP points to the beginning of the buffer. So the return address, not the return address. Oh, yeah. So when we do that, it's like the main function treats this piece here as its own stack frame, and the return address is here, right? The higher 4 bytes of the buffer. So if we move this one 4 bytes lower, then the first 4 bytes can be the return address. That should also work. Let's try that. So which means this one we need to move 4 bytes lower, and this one we point to the sharecode address. Then the middle 4 bytes we don't really need anything. Okay, make sense? We're not getting it. Any mistake here? What? Oh, yeah. I somehow deleted that print statement there. Okay, it also works, right? So, but you can see that I'm trying to rebuild the main functions. I'm trying to build the main functions stack frame inside this buffer. We don't have to do that. We can rebuild that in environment variable. Any other place we can control, right? So there are many different opportunities here. Okay. Okay, so let's summarize a little bit what we have done so far, why this attack works. I always encourage you to do that. Think about all the conditions that you need to pull off the attack. The reason is, as a defender, if you take out those conditions, take out one condition, you make the attack a little bit harder. It's difficult to come up with a defense approach that is perfect, cannot be defeated. But if you take out one condition, it always makes the attack a little bit harder. So far, we are injecting our share code onto the stack. One way or another, command line, environment variable, or buffer, they're all injecting the share code to the stack, which means we are injecting code to the stack. So the stack has to be executable. But the stack doesn't have to be executable. Why the stack should be executable anyway? On the stack, it's supposed to be data. We should never put the code onto the stack. Why it should be executable? So far that's our second condition. Also, we need to somehow overwrite the return address, or today we say that as long as we can overwrite the saved EBP address, we can still make this work. Okay. Also, we need to know our address of the share code. We don't need to know the exact location of the share code because we use a lobsled to loosen that requirement. So let's keep moving. So the first defense we are going to talk about is just to make the stack not executable. So today we'll show how that works and also show how we can bypass that. Like I said, the stack is not supposed to be executable anyway. So we just make it not executable. So this approach is called data execution prevention. You may see different names for it. All the CPUs we have right now support this feature. It's Intel, ARM, they all support that with different names, but generally we call it just data execution prevention. It means as long as that's a data section, for example stack, for example .data section, we can say this anything here should not be executable. Another name with it is W exclusive OR with X. Means as long as that section is writable, then it should not be executable. Basically, that's what it means. But it's a little bit, it's not very, what should I say? Some code can change itself, right? It can modify itself. To modify itself, like Java just-in-time compilation. It will generate a new code, compile it. When you compile it, you have to write that to the memory. Then you were to execute that, right? So it's a little bit conflicting with this. Some CPU call this just a long execution bit. Okay. So the idea of making data section not executable is not really new. At the very beginning of the design of computers, some people have been thinking about this. So most of the computers we are using now, we are using the von Neumann architecture, which means the same memory. So when I say memory here, it's a very generic idea of memory. It could be CPU cache. It could be your main memory, DDR. It could be SRAM. It could even be hard disk. So this is a general idea. So the same memory and the bus to collect the memory and the CPU, they can be used to store both data and code at the same time. So that is a von Neumann architecture. So the good things about this architecture is it's easier to implement. You just treat data and code the same. You don't have to implement separate bus, separate circuit for data and code. However, the problem you can see is it's not secure, okay? Because you can mistreat data as code. You basically mixing the control channel and the data channel. So another architecture is called the Harvard architecture. Some of the CPUs we are using right now are actually Harvard architecture. So some of the embedded systems might not be used, they are actually Harvard architecture. So I think ARM Cortex-M, M3, M4, they may be Harvard architecture. So the code and data code and the programs, they are stored at different memory locations. And there are separate physical bus circuit to collect them. The benefit of that is you can retrieve data and code at the same time. So it will be faster, but it's a little bit more expensive. And it's more secure. So, but because of this buffer overflow attack, or code injection attack. So far the attack we're doing is called code injection attack because we are injecting share code to the system. Because of that, in the early 2000s, most of the CPUs we are using, they introduce new features to the DEP feature. So before that, the memory permissions, there is only read, write, that's it. So as long as the memory location is readable, the memory region is readable, it implies it's also executable. Okay. Now we separate that, so we have read, write, and also executable. So AMD introduced a new feature, introduced the NX bit, not executable bit, in 2003. So that bit, I believe, is part of the memory page tables. So in the operating system, you have, in the CPU, you have something called a memory management unit, MMU. MMU refers to the memory page tables, which is located in the main memory, to split, to virtualize the memory for each process. And each process have many memory pages. So each page, there is a bit to tell if this page is executable, the NX bit. Windows starting to support this in 2004. Also, Linux started supporting this back in 2004. It's almost 20 years. So, so now when you compile a program, by default, the stack is not executable. If you want to make the stack executable, you have to explicitly use this option, -z executable exec stack, okay? So that is the option we have been using so far for all the programs. So if you look at our make file, so overflow return 4, that's the code we are going to revisit multiple times in the class. We set different, it's the same code, we just set different compiler options, and we're going to say how we can hack different versions of it. It's just getting harder and harder. And you can say you have been playing with overflow return 4 32. This is why you can say the flag we are giving it is M33, means this is a 32-bit program. Then there is a -F, no stack protector. So that is basically the stack cookie or stack canary protection, which we'll discuss next week. So we disable that. Then we have the -z exe stack. So this one makes the stack executable. That's why we are putting the share code there and we can execute that. Then today, what we are going to do is the second version, which you can say still 32-bit, still no stack pointer, a stack protector, but the stack is not executable anymore, which means you can still inject the share code in environment variable, but you will not be able to use that. If you jump there, you get a segment fault because that's not an executable section. After that, later we're going to look at the overflow return 4 cookie version. So this version you can say we're not giving it we're not disabling those standard defense anymore. So there will be stack cookies, the stack will not be executable, but we will know how we can bypass those defense. So if we compile this program with different flags, you can clearly identify that whether the stack is executable or not by using the readelf command. And you look at those are two different programs. Okay. So you can see this one, the stack is, this is a stack and it's executable because the permission is read, write, and executable. But with another program, it is not just a read-writable with no E there. Let me show you our server for the two challenges we have. We have, I should not do that, whatever. Let's say overflow return 4. The one you already hacked is this one. So we do a readelf. Let's just do all. I don't remember which option I should use. Then this is the one you inject a share code onto the stack. And you can say, here, the stack is executable, right? So today we're doing another one is overflow return for this one. No executable stack. So by the way, you can try your old exploit on the new challenge. So you can get a feeling, or you can even debug that. So you can say it doesn't work. Readelf. Here. Okay, for this version, stack is not executable anymore, only read-write. Okay, let's take a 10 minutes break. When we come back, we know how to hack this one. There is an attendance checking sheet if you are late, you sign up there. Okay, so we talked about DEP. What DEP does is it will say this memory region is data, and because this memory region is data, whatever here is not executable. But it doesn't really prevent you from overwriting the return address on the stack. It doesn't really prevent you injecting shellcode onto the stack. Even though after you inject, you will never be able to execute that, but you can still overwrite the return address on the stack. You can overwrite a lot of function pointers anywhere in the memory space. So a research direction right now, even what we're doing in our lab, is using new hardware features to protect all those code pointers. And for example, ARM introduced a new feature called the pointer authentication in just the recent 2 years. It's called PAC, P-A-C, pointer authentication. It's a new CPU feature. So it will basically sign all the pointers, and whenever that code pointer is used, it will authenticate that using a little bit of crypto there. Of course, like all other security approaches, defense mechanisms, it will be hacked eventually. So this year, even that approach, that solution has been hacked. There is a paper called Pac-Man. Basically, they use a side channel attack, which we also will talk about in the last 2 weeks in the class. We'll talk about cache side channel attack. They use the cache side channel attack to bypass that pointer authentication feature. Okay, so we say PAC, then let's say DEP. So let's say how can we bypass that? So actually, the way to bypass that, I already taught you. I just didn't mention the name of that. The way we can bypass it is something called return to libc. Okay. So far we are returning to shellcode. What if we do not return to shellcode? We return to some shellcode is what we inject there, so it's a code injection attack. What if we return to some piece of code that is already in the address space? It's already in the address space. System says it is executable. We just return to that. Okay? We do not inject new code to data section. Okay. So this is approach first discovered by Solar Designer. Obviously, that's a hacker's pseudonym back in before 2000. Okay, so if you just Google this, eventually you can find who he is. You can find a picture. A lot of new attacks were discovered by people with some pseudonyms, but because some of the attacks has been so successful, everyone knows who they are. So the idea is very simple. We just return to C library functions. Okay, we do not have to return to shellcode. And one of the C library functions that was very, very useful before for hackers was the system function. So in C library, there's a function called system. And for this function, it can execute any commands for you. And the first commands you want to execute probably is just being sh. Right? You can also do a cat here, then it will execute the commands for you. But right now, this approach doesn't really work on our system, on our server. You can still create the new shell, you can still cat, but you don't have the permission to do that because the system one, the system one basically will create a new process, and that process doesn't inherit the permission the parent has. I will show you how this works, but we will not be able to get a flag, but we will be create shells and we will execute commands. So the idea is very simple. Like I said, you just return to the C library function system. So you still have the return address up there, and you basically, so previously we were return to what? Return to print secret. And when you return to print secret, you give it parameters. Now you do not return to print secret, you return to system. And you give it a parameter, which is the string's address, being sh, like this. So actually, you already know how to do this, right? So we are going to hack the non-executable stack version of Overflow 4. Let's see how it works. Yep, this is a program. So the first thing we want to do is we need to get the address of system, right? Because we are going to return to system. So how do we get the address of the system? Many ways. The easy way is I just debug the program, I run this program. Then, when this program executes, the C library is also loaded into the memory space of this program. So I just use a command P in GDB, means print. So I just print system. Then it shows me, hey, this is the address of the system function. Well, we can also print the address of main function. We can also print, do we have a Overflow? Yeah, Overflow, right? So the same thing. So now we know the system is at this address. Let's write it down. Let me just copy this. This address is at here. This is the sys address. Then what is the argument we want to give to sys? Let's say we want to get a shell, right? So we / bin sh. So that is not a code, right? So we can't inject that in the environment variable, or it's actually already in the environment variable because remember, there is a shell environment variable, and also there could be other copies of it. So we're not going to injecting that. We just find it somewhere in the address space, so we can use the find command. Let's narrow down. So info files can show us all the different modules in this program when debugging it. Or you can see that at the beginning we have those program modules like elite, text, that's for the own program, and also we can show other modules loaded here. For example, the loader is loaded there, that's a loader, and so loader have different sections, text section and read-only other things. If we keep looking, we can also find the C libraries. So this is the standard C library is also loaded here, and we know their address. Starting from, there's still loader. Here, starting from this one, that's standard C library. So I believe there is that string in the C library. So let's just do a find. So how does it work is that's the start address we want to search. Then this is the end address we want to search. Oops. And from there, we're going to search the string bin sh. Yep, we do find one. So at that address, that should have the string bin sh. So we can examine that. So how do we examine? How do we examine memory? Which command? X, right? So with X, we examine, let's say just one string. So we do 1, the S, that means we want to examine one string at the memory location here. Should I have a star? Oh, no, I don't need a star. Okay. So see, now we examine that. It has that string we're looking for. So let's copy that address. That's, oops, what's going on? So here we have, this is the bin sh. Okay. So, Which buffer do we need for this one? Don't remember. So this Volfu, the EBP, let's say, it's at EBP minus 30, which is 48. So we need 52 bytes. So this runs from get, so we're going to pipe this into that. So our share code should look like Python 2. We need 52 bytes of garbage, then 4 bytes of return address. That return address should be 30, 55, well, sorry, 58, E1, F7, right? So after that, because this is the same as return to secret, so after that, another 4 bytes of garbage, right? That is return address for that system function, so which we don't care where it returns to. So that's another 4 bytes of garbage. Then after that, we have the parameter for system, which is that strings address, which is 52, 23, F6, F7, right? Yeah, looks correct. So that is just the strings address, 52. Okay, looks good. So we pipe that into the program and giving us a segment fault. What did we do wrong here? Oh, this is a shell. So we need to, this one we're trying to get a shell, so we need to do a cat there. Okay, let's see. Let's say if we have a shell. Oh, we do have a shell. Okay? We got a shell, but this is not a privileged shell. We're not root. We're just the user CTF. So we cannot really cat the password. When we do cat flag, we don't have the permission. Okay? So that's because we return to system, and the system creates a new process, and that new process doesn't have the privilege. Yeah. This one? That's the address of the string. What? Oh, this 52. That's the buffer. The buffer is 30 in hex. EBP minus 30 in hex. 30 in hex is 48 in decimal. Then another 4 bytes for saved EBP. So 52 in total. Yeah. So if we find another library function that can directly open a file and print out, then we should be able to get it, right? So we do not have to return to system. So even for system, there is another thing I want to show you is, let's say in a system we're not going to get a shell. We do not want to get a shell this time. We want to use the system to execute the cat command. So how do we do that? Let's say we want the system to execute cat flag. How do we do that? Yes, but that bin/h we find on the address space is already there, right? So for the cat flag, how do we inject that? We use an environment variable, right? So what we can do is we can export. What's the syntax? Should I use $? Beginning of this. Oh yeah, we don't need dollar sign. Dollar sign is just for. So what we can do is we do, let's say we call it just payload, whatever. Payload, then the payload would be a string. It's cat flag. Okay, so we can get where it is at. Payload. Okay, it's at that address, but that address is the program get environment says it, so it's not necessarily the accurate address, not the exact address. Then when we do that, we just need to change the, so this one is the address of the sys function, so we don't change that. We only need to change here. But here is a problem, you say, because we don't know the exact address of that flag. So when we do not know the exact address of the shellcode, we use a notepad, right? So here we also want to use a notepad, but what should be the notepad here? That's a notepad for the command, for the string. Something equivalent to a notepad. What should we do? Okay, good. We just use space, right? So let's say we put the exact location there, which is B7, D8. Technically, B7, D8 should point to if both programs, those programs, the target program and get environment, they have this exactly same location, that address still doesn't points to our string. It points to at the beginning of the payload, points to here. So anyway, it should not supposed to work. We don't need cat anymore for this one. So when we do that, the system function is called, but it's not creating a cat flag process for us. Then the shell says, I do not find the command, whatever command that is. So if we add several bytes there, let's say 6, 7. Let's add 7 bytes there. So what is 7 plus 7? 7 plus 4 or 14. 14 is what? E? Yeah, 14 is E, right? Let's see if it works. No, still doesn't work. Hey, it says K, okay. Now we're pointed to somewhere K. That's weird. We don't have a K here. Okay. That's why you can say even this approach, we want a knobsled. So the knobsled may look like this. We put a lot of white space, okay? Then we pass the whole line to the system. We hope the system where the address we're passing will be middle of here, right? So the white space doesn't matter, then eventually there will be cat flag. But still we get a permission deny, of course. Let's say the now we try this again. Okay, then not correct. Then we make it a little bit bigger address. We don't have a big sled here. Let's just try E maybe. Still not correct. Let's say where are we? Oh, then we should put that address again. So D856. Okay, we're too big here. 65. So maybe 78 looks good. No? Oh, sorry. The first 2 bytes, the most significant 2 bytes, were seriously off there. Okay. Now you say, now we actually were able to execute that. We get a permission deny. Okay. So we were able to do that count. Okay. So as part of the challenge, you can find any other system C library functions we can call to directly get the flag without really creating a new process. As long as it create a new process, it will downgrade its permission. Even if we do a sudo, doesn't work. Let's say, for example, instead of doing cat flag, we do a pseudo cat flag. But the pseudo is already after new process is created, so it doesn't work. Yeah, it's still permission denied. But this one permission denied looks a little bit weird. Let's see. Okay, too big. 7F, 6F maybe. Okay, you can see. So we were able to execute sudo cat, but it says you don't really have the permission to do sudo there. Yeah. Okay, so that is how return to libc works in general. But you can see that there are new protection there to downgrade the new process. So this approach is not very useful anymore. And also this approach, as you can see, doesn't work for 64-bit with our current knowledge, because you need to set a parameter there, and parameter is in registers in 64. So after we learn return to return-oriented programming, we will revisit this return to libc 64-bit version to see how we can make it work. Okay, so you can say that to do return to libc, we do not really need the stack to be executable, and we do not need to inject the shellcode onto the stack. So another version, a more generic version of return to libc is something I keep talking about, return-oriented programming. So far, when we return something, we are still returning to the beginning of the function, right? We return to print secret. We return to a C library function system. Some of you, you returned to the middle of print secret. You return to print flag, right? So, but you are still returning to the beginning of an instruction, okay? So in return-oriented programming, the approach is much more generic. We are going to return to the middle of the instruction. So what will happen if we return? We can return to anywhere, including the middle of the instruction. What will happen? So for example, that instruction right now, it's push EAX. Let's say that instruction has 3 bytes. Now we do not return to the beginning of that, we return to the second byte of that. So the CPU will interpret the rest of the bytes as a different instruction. So the CPU, that's not a push EAX anymore, it's a new instruction. Okay, but because of x86 instruction set is very dense, we can find powerful instructions, we call them gadgets, in the memory. So that is what we're going to do in return-oriented programming. That's one of that was discovered. So that one basically generalized return to libc, so that's why it's called return-oriented programming. And that was discovered back in 2009. The paper was published in 2009, a little bit earlier than that. Someone else probably also discovered that. That's a very, very useful thing. One of the most important discoveries in the last 15 years in system security, I would say. Yeah, we will learn that. We will spend several weeks on that as well. Okay, so you can see so far, all our attacks, we call it control flow hijacking attacks. We're trying to hijack the control flow. No matter you want to redirect the control flow to your injected code or some existing code, you are diverting the control flow. So to defeat this kind of attack, there is another approach called control flow integrity. So every program, there should be some predefined legit control flows. If at runtime, the control flow is different from the legit ones, we encode it in the program, then we say some attack is discovered. To hijack control flow, what attacker needs to do is to change some code pointer, okay? the return address on the stack, the code pointer, a function pointer is a code pointer, the virtual table of the C++ struct class, those are code pointers. Because those code pointers, at some point, eventually, it will go to the EIP or RIP, which is a program counter. Usually, the attack is we overwrite those code pointers through some memory corruption vulnerabilities. So then control flow hijacking attacks, so far we have been seeing two categories. One is code injection attack. That's we inject the share code there. The share code, so far we're looking at is a very simple share code. We're just getting a share or just read the flag. The share code can be very, very complicated. It can be, so far we're looking at 30 bytes of share code. It could be hundreds of bytes, thousands of bytes. It can not give you a share, but also give you a reverse shell, right? Those kind of crazy things. Basically, you get an arbitrary code execution. So you can use your share code to do anything. Another one is called the code reuse attack. In this attack, we do not inject share code. We do not inject malicious code. We reuse whatever is already there, like that's the return to libc system. But that one is still reuse some code developed intentionally. Then return-oriented programming and jump-oriented programming. In those, we are returning to some random bytes in the memory that we can interpret them as some useful instruction sequence. Okay, so for the rest of the class, we're going to do a little bit CTF. There are 3 levels. We're going to do a maze over the wire. And I believe there are 6 levels. But for the homework today, you are only required to finish level 0. But for the next 2-3 weeks, you are going to finish maze 1 and maze 2. So let's see how many you can finish today. So use your computer to SSH into maze 0. The password is just maze 0. Your goal is to, it's the same as, what did we do last week? Behemoths, right? Behemoths. The same logic. You are trying to get the password of the next level. And, but this challenge here, we haven't talked about this. I just want to say if you can do it. It's not that difficult. It's not even very binary related, but we haven't talked about this. We are going to talk about this kind of vulnerability in the second half of the class. I think we're playing on the same server. I think their system is designed different from ours. So on our server, when you play at the same time, we create a container for each of you. So you're not going to interfere with others. But it looks like when they're not doing it, I feel we're interfering with others, this one. Because this one actually requires us to access a temp file there. We may need to change things for that temp file, but it looks like all of us are working on the file, changing things. Yeah, that's my feeling. For example, when I do this, now it's like this. When I run the second time, it's different. I'm not sure, is that because we're playing at the same time, or see, this time it's -1. This time it's 0, and we open that file. See? Yeah, then someone create another. Okay, I have to admit, I'm not sure what's going on because I played this years ago. I don't remember what's going on. We probably should not play this at the same time. Yeah, maybe you can work on the homework first. I will update you what's going on with this one tomorrow. So you can work on the challenges as well. Yeah, I'm removing that task. Yeah, just free 10 points. Yeah. Sorry, I should have tested this before. Last time I do this was, so the thing is, I actually want you guys to work on maze level 2, not maze 0. Maze level 2 is a buffer overflow, but they recently updated our system because, I believe it's because last time we DDoSed it. So after they update the system, we don't have the password for maze 2. So you have to start with maze 0. I don't have the password anymore, and technically I'm not, even if I have the password, I'm not allowed to share that anymore. So, so that's why I want you guys to start with maze 0, but I think maze 0 has some issues now. So yeah, let me get the password later for maze 2, then we work on maze 2, which is a buffer overflow one. Okay, update it.
use the some other address to get. But then if I run this challenge again, and I can still use the first the data.
Yeah. Well, I'm not sure what's going on there. I'm not 100% sure what's going on there. Yeah, because I didn't debug this. When we designed this, it was easier, a little bit easier than this. But what happens is we have been updating the underlying system, right?
Yeah.
So when we update those things, get a lot of things changed, but our code stayed the same. So, yeah, but yeah, I think you did good there. Yeah, that's the best you can do there. Yeah. Yeah.
Oh, okay. Thank you, Professor.
Sure. So are you going home now, or are you going home now, or? You still have your bicycle?
Yeah.
Okay.
For this project, I just first read this and then try to run that the code.
Yeah. Yeah, those are very high level stuff. You read it, you can fit it quickly. But you need to understand how pack works, right? Without understanding pack works, we can't do anything. Yeah.
Okay.